welcome.
Yeah. Thank you so much. And let me just begin by saying a big thank you to the organizers for giving me the opportunity to present what we think is a series of world firsts in the realm of room temperature quantum computing. And that is running actual quantum applications on fully integrated on-site room temperature quantum computers. So to give you a bit of context, I'm a quantum apps developer for Quantum Brilliance. And we work on quantum computers that operate, there it is, on diamond chips. That is, our qubits are realized by NV centers implanted in these diamond chips. And that allows us to create devices which are, relatively small in comparison to other quantum architectures you might know, that operate completely at room temperature and standard pressure. Right, so how does it work? Due to the shortage of time, I'll be limited today to talk only about the quantum chemical applications that we have tested so far. And therefore, let me give you a very, very quick introduction into quantum chemistry itself. The usual problem that you target in quantum chemistry is solving the time-independent Schrödinger equation here. And the usual ansatz to do this is to parameterize your wave function as a linear combination of many body states psi I, which in turn you parameterize as an anti-symmetrized product of these one particle states chi. And you can also make life a little bit simpler and represent this in three-dimensional space by having kind of the interaction potentials of your Hamiltonian on one axis here, the quality of the one particle basis, so this is the chi's on another axis, and the quality of your many particle basis on the third axis. Quantum chemists know this picture quite well, and well, it has this name cube of accuracy that's somewhere around there. And the usual target in that picture is to reach that outer edge here in the far right corner. That is then approaching what is known to be would be the exact solution, right? However, in most of quantum chemistry that's out there, you are limiting yourselves to just a small part of that cube, which is the so-called non-relativistic framework, so only including the non-relativistic interaction potentials of your Hamiltonian. And a natural way for quantum computing kind of to attack this problem is by finding approximations here, or finding good representations of these linear combinations of many particle functions by using superimposed bit strings representing these individual many particle states. And the usual way forward, or kind of the state-of-the-art approach that was out there, is the so-called variational quantum eigensolver. I'm sure you've all seen that once or twice, so let's make this quick. The general way this works is really, really simple. You start by a general qubit encoding where you kind of map your quantum chemical fundamentals to individual qubits, to your qubit register. Then you apply a parameterized ansatz circuit that hopefully creates the many particle wave function, or a good representation of the many particle function, of the full electronic wave function. And then you apply these basis rotations UL, which come from the Hamiltonian itself. So you decompose your Hamiltonian into Pauli tensor products, rotate to the individual bases of these Pauli terms, and then measure the expectation value of them in the computational basis, right? Then after measuring that, you classically, sum all of them together to get an estimate for your energy, and then have a classical feedback loop to your ansatz circuit here, and optimize the parameters in your ansatz circuits until you arrive at your lowest energy solution. Yeah, exactly. So you can immediately see from that kind of picture that there might be a problem here, because if you think about it, in essence, you create the same state over and over and over and over again, and looking at it from different perspectives to get all of these contributions, to the energy sorted out. There has been a lot of progress in the VQE literature that's out there in terms of minimizing, the resources of VQE and also optimizing the Ansätze, etc. Just to name a few, there's just different types of encodings that you can use. There's a gazillion different circuit Ansätze, which range from just hardware-efficient Ansätze to more chemically inspired Ansätze. And there's also a lot. Also a lot of work been done in reducing this basis rotation overhead in VQEs. Nevertheless, it's becoming clearer and clearer now that VQEs might not lead to the quantum utility that we all hope for. There's a very nice review article here by Tilly about VQEs, and they estimate runtimes for individual VQE iterations. And they make these estimations based on a 100 nanosecond gate time quantum computer, which is on the faster end of the spectrum, right? And estimated for a problem that is the dichromium molecule, which is kind of the smallest problem that's too hard for classical computers to solve anymore. And what they find is, unfortunately, a single iteration using the Rotosov algorithm takes 35 years roughly. That is not going to be practical at all. So therefore, we kind of thought about this and thought about what can you do different. Well, what we came up with is something that we call quantum wave function sampling. The general idea of wave function sampling is to not use the quantum computer to measure the energy, but rather use it in a sense of generative machine learning, where you learn a probability distribution that effectively represents the electronic wave function itself. So the general circuit structure is shown here, and it's basically composed of two fragments. One is just a VQE type segment that just applies your qubit mapping, and then a parameterized ansatz circuit on top of that. But then in contrast to VQE, does not involve all these different basis rotations, but just measures all of them once. And then there's a second component that has also been used in the quantum restricted Boltzmann machines, which is just a classical component. That is a single neural network node that takes in the classical bit outputs of all of these measurements and computes a phase value, so a sign for all of the contributions in the wave function. So let's go through this in a little more detail. So what would happen if you just take the left component and measure it? Well, you get your measurement statistics, right? And the problem with that is, of course, these will never actually represent an electronic wave function because the phase information is missing. There's no sign in probabilities. And therefore, we need that second component here, which you can train completely classically, right? It doesn't increase your quantum resources because it just requires the measurement outcomes, which can be trained to find an optimal phase value, so just plus or minus 1 for each of the bit strings by training these weight parameters here and the bias parameter here. And then what you do is you merge both of them to get the representation of the electronic wave function itself. Using that, you can calculate the energy classically and have the same feedback loop as in VQE into your parameterized ansatz circuit. Right? So in a more, just to write it down in a more detailed fashion again, you start with your standard encoding, just as in the VQE case. Then you do your sampling to get your measurement histogram from the parameterized ansatz circuit. You do the classical sign optimization of that classical part here. And one cool thing to note is this can either be done in serial, meaning that you do one iteration where you optimize both the circuit parameters and the classical sign parameters at the same time. Or you can have it in a nested fashion where you kind of do one iteration of the circuit, right? And then while the next iteration is running, optimize at the same time the parameters of your classical part in a nested fashion. So it's in a sense, highly hybrid integrated algorithm, if you do it that way. And then finally, you need to calculate the energy by evaluating the Hamiltonian expectation value to get their feedback. So one extremely cool thing about wave function sampling is that it's completely agnostic about the kind of Hamiltonian and the mapping to the quantum device, right? So that allowed us to actually use one of our prototype devices, which has 2 qubits, to run reasonably large calculations, and that is by using a very qubit efficient encoding, by encoding not orbitals to qubits, but encoding configuration state functions, which are linear combinations of Slater determinants, to binary numbers on the qubit register. So with 2 qubits, you could then span, so to say, 4 configuration state functions, which is a larger space than when you just use, well, for example, 4 spin orbitals usually. And you can make use of spin symmetry and all the good stuff to reduce costs as well. And so as I said, this is our prototype device. You can see it's just integrated in existing HPC infrastructure. It's just a server rack mountable device. It is, I think, 9U in height and is completely black box. It's really magnificent if you see it running. Just a few days ago, we actually took one of these devices out into the bush and did tests there, just in a parking lot. Magnificent to see that. There's a blog article on LinkedIn if you're interested. And here are the results of the wave function sampling. So the first row is just the classically exact energies, so from exact diagonalization. Then we have complete active space CI energies, which uses the active space approximation to make the space smaller. So these are our classical reference energies. Our quantum algorithm cannot be better than those. In the hydrogen case, well, these numbers would be identical. And then we have wave function sampling just done on an ideal classical simulator. And as you can see, the numbers perfectly match, which is kind of the proof of concept that it's working. And then most interestingly, we have the actual results from this device here. And as you can see, for H2, with only 100 shots, we are within chemical accuracy, so we have extremely good results there. And for the 2-qubit circuits, with 500 shots, we are almost there. We are not quite within chemical accuracy, but we're closing that gap by the day and hopefully arrive there soon. Right? And before I close my talk, I was asked to do a little bit of advertisement, and that is a new series of web tools that are being developed at Quantum Brilliance, coined under the name Crystal Lab. Please feel free to try them out. They're still in development status, so if you find anything that's not working, let us know. And one part of that Crystal Lab suite is the so-called Utility Explorer, which allows you to find out a little bit more about wave function sampling and also run a few small test applications directly in the web browser, as well as do resource estimations for wave function sampling in terms of runtime accuracy, and for this conference, probably most interestingly, energy consumption, and in which problem range roughly you could maybe expect an advantage if you scale that up. Right? And with that, I'd like to close, and thank you very much for your attention.
Any questions? Sure.
How accurate do the measurements need to be throughout the whole process?
Well, as accurate as you can get them. It's different.
Some threshold beyond which it fails if the accuracy drops
So that is something we are currently investigating, and it seems that the dominating effect in terms of accuracy is the shot number induced cutoff in the wave function. Right? If you have coefficients of your wave function that are very, very small, and you have a lot of them, for example, then if you introduce a finite number of shots, there's a high probability you might miss them. That is currently the largest impact that we see.
One question I have about VQEs in general, I'm wondering how it applies to your scheme. Is it a common criticism is that you're optimizing over a potentially very large optimization space, and these kinds of things tend to get stuck in barren plateaus with exponential time to convergence? And so does your approach have the same problem, or does it avoid it somehow?
It's a good question. We don't know yet, but there's at least hope, because since we only require the actual probabilities representing the wave function coefficients, we do not need to nail the specific real coefficients of the wave function on the qubit register. So we can imply or use simplifications on the circuits themselves, which may help with that, but we don't know yet.
All right, well, keep us posted. Thank you very much. And please join me in thanking Nils again.